So, ladies and gentlemen, you are all welcome to my YouTube channel. My name is Mukhtar Aliyu. So, today we are going to look at the concept of solubility product and common ion effect. And this PowerPoint is not made by me, it's made by Dr. Arun Sharma, MSc PhD from RPSC set. So, I'm going to make use of this PowerPoint to make my presentation. So now let's start with the solubility product. So the solubility product of strongly soluble electrolyte is equal to the product of ionic concentration in a saturated solution at a given temperature. So when we are talking about solubility, generally we have different types of solid substances. We have soluble solute, we have insoluble solute, and we have partially soluble substances. So when you have a strongly soluble electrolyte, that is a partially soluble electrolyte, is the product of the ionic concentration. So the solubility product of strongly soluble electrolytes is equal to the product of ionic concentration in a saturated solution at a given temperature. So we should understand that a solubility product is equal to the product of the ionization of the concentration of the product of the reaction at a given temperature. So and generally ionic compounds tend to be soluble in water because water is a polar solvent and stabilizes the separated ions. So now, let's look at this example. So an equilibrium can exist when a partially soluble substances and its solution exists. So when there is actually an equilibrium exists, or equilibrium can exist between a partially soluble substance and its solution. So we should understand that it is in this situation where we have equilibrium exists, when we have a partially soluble substance and its solution. So this is when we have the equilibrium. Like for example, here we have AB solid substances and it dissolved to produce A ion in aqueous solution, then plus B negative. That is both cations and anions. So the solubility product is equal to the concentration of these individual ions. That is how we measure it. And it usually exists, or its usual equilibrium position usually exists when you have a partially soluble substances and its solution. So now let's look at a salt here. A salt here is initially put into water and begins dissolving. So the salts will continue to dissolve. However, the dissolved ions will also precipitate. You see, at the same time as the salt is dissolving, of course, when salt is dissolving, and ions are usually produced. So, but as the salt continues to dissolve, then the ions generated during the solution, they will start precipitating because the salt dissolves faster than it is ions precipitate. So the net movement is toward the solution. So it means that as the salt dissolve, then at the same time the ions form are also precipitating at the same time, and eventually the rate of dissolution will be equal to the rate of precipitation. Therefore, the solution will be in equilibrium, but the ions will continue to dissolve and precipitate at the same time. So it means that this is a dynamic equilibrium. It is a dynamic equilibrium where in a saturated solution, the salt is dissolving and at the same time, the ions generated are also precipitating. So it is a dynamic equilibrium because the solution continues and then precipitation also continues. So precipitation and the solution are happening at the same time, but the partially soluble substances exist in equilibrium between its solution. So that is what we call equilibrium. It's not that the system is static. It's not that the system is not moving. No, the system is moving, but there is a change, but it maintain or it still maintain equilibrium. Like for example, here the solution is taking place, and then at the same time, precipitation is taking place. So the precipitation and the solution are taking place at the same time, and that is why equilibrium position exists. So in saturated solution, dynamic equilibrium exists between undissolved solute and the ionic species in the solution. So solute continue to dissolve and ion pairs continue to form. Then at equilibrium condition, the rate of the solution process is equal to the rate of precipitation process. So I think this is very clear. It happens when you have a partially soluble substances, and then the partially soluble substances is dissolving to generate ions, and the ions at the same time are precipitating. So the solution and precipitation are taking place at the same time, and that is why equilibrium position exists. So the next thing now is to look at, or is to check on the solubility product expression. So like now look at this. Here we have the partially soluble substances. So it ionizes. It's of course it really ionized to generate A as a cations and B as an anion. So after generating this, then of course we also have B here. So A ions and B ions are generated. So to get the solubility product is represented as KSP. And of course, it usually, or it measures only the concentration of the reactant, which is the ions that are generated. So these are the ions that are generated, and that is why the KSP here is measuring the concentration of A here, and then the concentration of B. And then so since A is just 1 mole and B is only 1 mole, and then is of course here we have S solubility, and then S solubility. S times S is going to give us S square. Then at the end, to get the KSP, then you can now make S subject of the formula. How do you make S subject of the formula? Of course, remember we have KSP here, then it's equal to S square. So to make X subject of the formula, you can just take square root both sides. So this one will now kill this, or will now cancel this. So we now have S is equal to square root of KSP. And of course, square root of KSP, whenever we have square root, is the same thing as 1 all over 2. So that is why we actually have this expression. Make the concentration of the substance of the ions subject of the formula. So the solubility is always expressed in mole per liter. So we should know it is in concentration. So the solubility here is always measured in mole per liter. It's always measured in mole per liter, which is this. And then for the solubility and for the soluble electrolyte, it is expressed in terms of gram per 100 gram of the solvent. So now there are 3 conditions. So when the concentration of the ions, when the concentration of the ionic product is less than KSP, it means that the solution is unsaturated solution. And if the concentration of the ionic product is equal to K solubility product constant, it means that the solution is saturated solution. And then when the concentration of the individual ions, when the concentration of the ionic product is greater than that of the KSP, it means that the solution is oversaturated. It's oversaturated solution. It means that it is precipitate. So KSP is also known as a solubility product. It is also known as solubility product. So now the next thing is to see how we have this solubility product for uni type of electrolyte. So this is uni type of electrolyte. Because why do we call it uni? Because the silver chloride dissolve to give 1 mole of silver ion plus 1 mole of chloride ion, and that is why it's called univalent type of electrolyte. So what is the equilibrium constant? How do we get the equilibrium constant? So because it is 1, so of course we are going to take the concentration of silver then times the concentration of chloride ion. So that is why at the end we have Ksp is equal to concentration of silver times concentration of chloride ion. So they are the same. So the solubility concentration is now going to be S times S. So S times S is equal to S square, and that is where we have this. So now what about the value of Ksp? What will be the value of Ksp? So assuming now we have the value of Ksp here to be 1.6 times 10 raised to the power of minus 10. So how can we calculate the solubility? The solubility of the ionic form. So you see, since here we have S square, and then of course we have Ksp. So it means that Ksp is equal to S square. So how are we going to do the calculation? Is simple. Since we know that the Ksp is equal to S square. So of course the Ksp is given as 1.6 times 10 raised to the power of minus 10. That is equal to S square. So to get this S, you just get the square root both sides, and then you now make the subject of the formula. And if you now take the square root of 1.6 times 10 raised to the power of minus 10, it is going to give us 1.3 times 10 raised to the power of minus 5 mole per liter as a solubility. So this is for univalent type of electrolytes. So let's look at another example. So in the situation where we have bi-univalent type of electrolyte, so look at it here. 1 mole, we have magnesium hydroxide. So 1 mole of magnesium hydroxide dissolve to produce 1 mole of magnesium and then 2 mole of OH minus. So therefore here we have 1 mole, so that is why it's called bi-univalent type of electrolyte. So therefore now here we have magnesium as a divalent ion here, or bivalent ion, and we have OH as a monovalent. And of course, to get the concentration, this one is 1 mole. So here, that is why here we have nothing indicating 1 mole. And here we have 2 mole of this, so that is why here we have 2 mole. So here we have 8.2 times 10 to the power of minus 12 as the value of a key. So the value of key here, that is the Ksp is 8.9 times 10 to the power of minus 12. So if S is a solubility of magnesium hydroxide, then magnesium is going to be S mole per liter, S mole. And then for the, of course, for the OH minus is going to be 2 mole because it is 2 mole we generated. So that is why here we have 2S mole. So for the magnesium, we have only S because it is 1 mole and there is no any number of moles here. So that is why it's only S. And then for, of course, for OH here is 2 mole. It is 2 mole. It is 2 mole. So because it is 2 mole, so that is why here we have 2 mole of it. And of course, the coefficient is 2. So that is why we have raised to the power of 2. So we are now going to have 2 square is 4. Then we have 2 square times S here. Then we have 4S raised to the power of 3. And this gives us 8.9 times 10 raised to the power of what? Already we know this. So now we wanted to get the value of S. We wanted to get the value of S. So since we know that our Ksp is given as this, so it's just now going to be Ksp is equal to 4S raised to the power of 3. So therefore, to get S here, because we already have this 8.9 times 10 raised to the power of minus 12. So here is 4. So we have to say divide both sides by 4 here. And here it will be left with s raised to the power of 3. So we have to make this subject of the formula, that this s raised to the power of 3. So we have to have something like this cube root here. And then here cube root. So this one will now cancel this. So after you press your calculator and everything, we are now going to have 1.3 times 10 raised to the power of minus 4 mole per liter. So this is for bi-univalent type of electrolytes. And then the next example is for uni-trivalent ions. Uni-trivalent ions. So you see, in this case, you have silver, and this silver phosphate dissociates to generate 3 molecules of silver ion, and then 1 mole of phosphate ion. So now, here is 3, so we have silver ion as raised to the power of 3 because the number of moles here is 3, and here is 1 mole, so that is why we have only 1 here. And of course, the KSP, that is the solubility product, is 1.8 times raised to the power of minus 18. So if S is a solubility of the silver phosphate, then, so here, since this one, silver is 3 mole, so that is why it's going to be 3S, and this one is 1 mole, so that is why it's going to be S. So this is the 3S for silver, and of course, the 3S, the power is going to be 3 because the stoichiometric coefficient is also 3. So that is why we have 3S open bracket close raised to the power of 3, and then we have S. So then we now have this. So S raised to the power of 3 is S power 3 times S. So that is where we have S power 4, and we have 3 here. So 3 raised to the power of 3 is the same thing as 3 times 3 times 3, which will actually give us 27. So that is why we have 27 S raised to the power of 4. So to get S here, that is the solubility. Of course, we have KSP. KSP is now equals to 27S raised to the power of 4. So of course, we have to make the S subject of the formula by dividing both sides by 27. So this 27 will now cancel this, and of course here it will be going to be fourth root, and this one will now cancel this. So at the end, we are going to left with S with K square fourth root or fourth root of KSP divided by 27. And if you actually use your calculator, you are going to get 1.6 times 10 raised to the power of minus 5. Okay, and then so this is for univalent. So for trivalent, univalent. So you see here we have when this, okay, trivalent, univalent type of electrolyte. So you see in this case you have chromium hydroxide, so it's dissociates to give 1 mole of chromium 3, and then 3 mole, and then 3 mole of OH. And of course, this is trivalent and this is monovalent, but here we have 3 mole and here we have 1 mole. And of course, the KSP here is given as 6.7 times 10 to the power of minus 37. So if the solubility product is S, then how are we going to get S? So for S here, because it is actually trivalent, but 1 mole, only 1 mole, that's why we have S. But here is 3, so that is why we have 3 mole, and the stoichiometric coefficient will be 3. So that is why we have 27 S raised to the power of 4 is equal to 6.7 times 10 to the power of minus 37. So you just make S raised to the power of 4 subject of the formula and get your answer. And the answer here will be 1.3 times 10 to the power of minus 18. So then let's look at another scenario. So for bi-trivalent ion, we have calcium phosphate dissociates to produce three molecules of calcium ion plus two molecules of phosphate ion. So of course the KSP, we do the expression. We have calcium ion in bracket because it is 3 here. So we are now going to have power 3, and of course here is 2, so you have phosphates and then you have power 2 is equal to 1.3 times raised to the power of minus 37. So if the solubility is S, how do we do that? So now because here is 3, so that is why we have 3S, and then here is 2 mole, so that is why we have 2S. So of course the coefficient here is 3, so that is why we have 3S raised to the power of 3. And the coefficient here is 2, that's why we have 2s raised to the power of 3. So everything here will now give us 108 raised to the power of 5 is equal to 1.3s. So you now make S subject of the formula from here, and then we now have the final answer as the solubility is equal to 1.6 times 10 raised to the power of minus 7 raised to the power of minus 7. 1 So let's look at so this is actually the general expression. In general, this is the general expression. In every situation, when you have your solubilization or dissolution, you can use any of this and get your answer. So you see, this is A x by. So after dissociation, it's going to give us x a raised to the power of y plus, and of course y b raised to the power of x minus. So the solubility product is now going to be KSP is equal to a power y plus the concentration bracket for x, then concentration bracket of bx raised to the power of minus x, you close the bracket for y, and at the end you have this and this, then you multiply them, then you now take x raised to the power of x, y raised to the power of y, and then of course it is going to give us the final expression. So this is the final expression. This is how to do the expression from the previous slide. So this is like a general expression, Let me just give an example here so that it will be much more easier. Let's say here we have calcium chloride. So we have calcium chloride. So when calcium chloride dissociates, to give calcium plus then plus 2 molecules of chloride. So now this will be your X, this will be your A, this will be your A, and of course here, because there is nothing, so it's 1 mole, so this one will be your X, and then this raised to the power of 2 will be your Y, and then 2 here will be your Y here, and then X by minus here will be this, and then chloride will be this. So you use this general expression and make every expression, and then lastly you make the S subject of the formula. And I think this one is simple, so you should actually understand how to do that. Of course, we have done that, and it's something. This is just a general expression. So I think it is the right time to start to look some examples here. So now, but before we move there, what is solubility and KSP? So there are 3 important definitions that you need to know. So the solubility actually is a quantity of substance that dissolve to form a saturated solution, while molar solubility is the number of moles of solute that dissolve to form a liter of saturated solution. And then we have KSP, which is solubility product, the equilibrium constant for the equilibrium between ionic solute and its saturated solution. So, and I think for the KSP, we make this definition. So when we say solubility, it means that it's the amount of a substance that dissolves in any solvent to form a saturated solution. Yeah, for example, is it a salt, maybe sodium chloride, then you dissolve it to form a saturated solution. That is solubility. And then the molar solubility is just the number of moles of the solid that dissolve to form a liter of saturated solution. And then we have KSV. So these are the three important definitions in solubility and solubility product. So some values for the solubility product constant at 25 degrees centigrade. So these are some of the inorganic compound. We have barium hydroxide, aluminum hydroxide, barium carbonate, barium sulfate. There are so many of them. Their solubility, equilibrium, and then their individual solubility product. So write the expression of KSP of the following silver chloride. So you just dissociate. After it dissociate, it will give silver ion and chloride ion. And of course, the expression will be the concentration of the ionic product. And of course, for the late iodide, the something, and for calcium phosphate, the something. So this is simple from previous explanation. This is simple and I think it's clear. And then, so now let's look at some example. If a saturated solution of barium sulfate is prepared by dissolving solute barium sulfate in water, and of course we have barium ion, the concentration of barium ion is given as 1.05 times 10 to the power of 5 minus 5 mole per liter. So what is the KSV for barium sulfate? So first you have to take barium sulfate and then dissociate it. So the barium sulfate dissociates to produce barium ion plus sulfate ion, and all of them they are 1 mole. So therefore the KSV is equal to concentration of barium chloride times concentration of sulfate. The bracket means concentration. So they are the same. So let's just assume since they are the same and they are 1 mole, so you can just say x times x. So we have x squared, that is solubility. So if x of barium chloride is equals to the x of sulfate, it means that it is the same thing as 1.05 times 10 to the power of minus 10 given from the question. So now to calculate the KSP, then we are now going to have KSP is equal to 1.05 times 10 to the power of minus 5, of course, square, because the concentration of barium chloride is equal to the concentration of sulfate ion. So they are the same. So that is why it's going to be square. So x times x, so it's x squared. Then we now square the KSP value. So we now square the concentration values, and then we get the value of our KSP as 1.1 times 10 raised to the power of minus 10. And I think this one is also clear. So now the next thing that we are going to look at is common ion effect. So the separation of the dissolution of weak electrolytes in the presence of strong electrolyte having ion common with that of the former is known as common ion effect. So when you have separation of association of a weak electrolyte in the presence of strong electrolytes having an ion common with that of the former is known as common ion effect. So generally, as we said, equilibrium is achieved when you have partially insoluble solutes or weak electrolytes. So when you have another salt or another strong electrolyte that have an ion, and the ion is common between the dissociation solution or the dissociation weak electrolyte or the partially soluble electrolyte. So that ion that is coming to now reduce or suppress the dissociation of the weak electrolyte. So that is what described as a common ion effect. Like, for example, consider the following equilibrium. So in this case, you have silver chloride breakdown to produce silver ion chloride ion, and the KSP is 1.6 times 10 raised to the power of minus 10. So the solubility of silver chloride is 1.3 times 10 raised to the power of minus 5 mole per liter at 25 degree centigrade. If sodium ion is added, then the equilibrium shifts left to increase in chloride ion, and then some silver chlorides will precipitate out. So you see, in this case, you have silver chlorides, and now you add sodium chloride. So as a result of adding the sodium chloride, because the chloride ion is common, here there is also a chloride ion. So here there is also a chloride ion. So you are now adding this. So adding this will now decrease or suppress the dissociation of the silver chlorides. So as a result of that, the equilibrium will shift to the left due to increase in chloride ion, and some of the silver chloride will be precipitated out. So as a result of that, there is a separation of the dissociation of the silver chloride, and this is what described as a common ion effect. And the separation is due to the common ion, which is chloride ion. So that is what described as a common ion effect. Then the next thing is the common ion effect on solubility. So the presence of common ion decreases the solubility of a slightly soluble ionic compound. Like for example, here we have late tetrachromate 6 associates to produce lead ion and chromate ion. But now if you add sodium tetrachromate 7, so and this one is a very soluble salt, a strong electrolyte. So as a result of that, according to Lechacheles, then the equilibrium will shift to the left. Therefore, the effect of a common ion on solubility. So let's look at this one now. Here, this is what you have. You have two fragments. You have precipitates at the bottom, then you have the solution. But now you add chromium 2, or you add sodium tetraoxochromate 6. So what will happen? Look at the upper part. The upper part is precipitating. So therefore, the dissolution is decreased while precipitation increases. So this is what we describe as a common ion effect. So this is the end for today's class, and I hope if there is any, and I hope that you will be able to solve most of the questions. And if this is the first time you are coming to my YouTube channel, please subscribe. Please subscribe. Thank you.